Welcome back to the ChemDoctor, and this would be the third video on the playlist on solubility equilibrium, third or fourth video actually. Alright, now what we're going to do is we're going to start to put a number of different concepts together involved in this particular problem. And what's going on here is we're taking and we're mixing together two solutions that contain common ions that are involved in a solubility equilibrium. So we're going to mix together 300 milliliters of a 0.01 molar solution of sodium carbonate and 100 milliliters of 0.01 silver nitrate. Both compounds are soluble. I'll draw a picture quickly of what we have going on. So we have a beaker, and in the beaker we have a total of 400 milliliters of solution, right? Because we're adding the 300 mLs to 100 mL, so there's 400 total mLs of solution in the beaker, and we're mixing two completely soluble compounds. So unlike the previous examples that I've taken the viewer through, in this one we're not starting with a powder on the bottom of the beaker. In this case we're starting with silver ion in solution, and we're starting with carbonate, which is also in solution. And so therefore the question is the following: will a precipitate form? And if it does, what will be the new solubility of the compound, given the equilibrium expression I have over here on the right, where the equilibrium constant for the solubility of silver carbonate is 8.1 times 10 to the minus 12th. So silver carbonate is the solid or the precipitate that you would expect to form on the bottom of this beaker if the concentration of the carbonate and the silver are in the right proportion to cause the equilibrium to shift towards formation of the solid. Alright, so how are we going to figure this out? Alright, the first thing we got to do is figure out what the actual molarities of the silver nitrate and the sodium carbonate are in this new solution, because the volume is now 400 milliliters instead of the volumes in which these two things were originally combined. In other words, we had 100 mLs of the 0.01 molar silver nitrate, and we had 300 mLs of the sodium carbonate. We've mixed these together, and we've produced a new volume. So that means the molarity of these two solutions is going to change. So the first thing we got to do is figure out what the new molarities are. And then the second thing we're going to do is we're going to calculate a Q. So maybe we should make a list. All right, number one, we're going to calculate, and I'm going to abbreviate this, we're going to calculate new molarities. Okay, the second thing we're going to do is we're going to calculate a Q value, because we need to know whether or not the reaction is going to shift to the left or the right. So left or right. Alright, if the reaction shifts to the right, we're done with this problem, because what that means is there's not going to be any precipitate in this beaker. If the reaction shifts to the left, then we're going to have a solid forming in the bottom of the beaker, and we're going to have a solubility equilibrium that forms, and we're going to need to calculate the concentration. Well, we're going to need to calculate the solubility. Let's just boil it down that way. So we're going to be calculating solubility depending on Q. Alright, so that's the list of the things we got to do here to figure this problem out. So let's go ahead and get started. So we're going to have, to find the new molarity, what we're going to need to know is how many moles specifically of each one of these two things we've got, and then we're going to divide our new moles by our new volume. So how do we find that? Well, alright, so this is kind of old material, but basically you've got a volume and you have a molarity. So to find the moles of the sodium carbonate, we're going to convert the milliliters of the volume to liters, so it'll be 0.3 liters. That's just simply taking 300 and dividing by 1,000 mLs. and we're going to multiply the volume times the molarity of the salt. And the molarity, remember, our molarity are units of moles per liter. So it's going to be 0.01 moles per liter. And you can see here that your liters cancel out. And what we're going to get for the moles of the sodium carbonate will be 0.003 moles of sodium carbonate. And similarly, for the silver nitrate, similarly for the silver nitrate, we're going to have 0.1 liter instead of 0.3, so it'll be 0.1 liters, and it will be times 0.01 moles of silver nitrate per liter. So we're going to end up with 0.001 moles of the silver nitrate. Now, to find the new molarity, we're going to divide by the new volume, which is 0.4 liters in each case. So the new molarity of the two salts will be 0.0075 molar for the sodium carbonate, and for the silver nitrate it's going to be 0.0025. This is the new molarity. Now we need to find our reaction quotient, and remember that Q is calculated exactly the same way as the equilibrium expression. Maybe I should write that over here on the right, the equilibrium expression, so everyone's clear on what the expression looks like. So for this precipitation equilibrium, the KSP will be equal to square bracket silver raised to the second power for the coefficient, all right, and then times the carbonate. And the carbonate's raised to the first power because the coefficient in the equation is 1. All right, so we're now going to calculate a Q value using the same expression, however plugging in these non-equilibrium values, and we're looking for a magnitude number here. We're looking for a number that we can compare to the KSP value of this reaction, which is 8.1 times 10 to the minus 12th. So the concentration of the silver is 0.0025, and that concentration is going to be squared. All right, and then we have the concentration of the sodium carbonate, which is 0.0075, and so the grand total here is going to be 4.7 times 10 to the minus 8th. Now, 4.7 times 10 to the minus 8th is a bigger number than 8.1 times 10 to the minus 12th. So our Q value is greater than our KSP. And that means your reaction shifts left. All right. Now, what that means is that we're going to form a precipitate. So to be clear about that, I'm going to go ahead and this precipitate is going to be a white one. I'll use gray here to color it in, just to emphasize the fact that we're actually going to form a solid. So I'm going to put this in the bottom of the beaker now. So now what we got going on here is a solubility equilibrium, and we're going to need to go ahead now and calculate the solubility of the silver carbonate. Only there's a twist here, because we've got two different concentrations of reactant, and one of them's a limiting reactant. So they're really throwing a curveball at us with this one. So what we're going to have to do first, before we can get onto the solubility calculation, is actually figure out a limiting reactant. And that's a stoichiometry problem, where we're going to be assuming 100% reaction. All right, and what do I mean by that? So we're going to have we're going to have silver ion, which is combining with the carbonate to form the silver carbonate. And we need to figure out which one of these two things is the limiting reactant. Now, the way I set this problem up originally, when we calculated our new molarities, is I broke these down into steps deliberately so we could come back here and we could collect the moles of each one of these things that we've got, because I anticipated we were going to have this issue with the limiting reactant. Now, your teacher may have trained you in a lot of different methods on how to do this, but in my classes I basically insist on the method that we're about to use for this. And some of you are probably comfortable enough with this that you can look at these two values right now and you can see which one's the limiting reactant. But if you're like I was when I first took chemistry, you're going to look at these two values and go, man, I have no idea. So here's how you figure this thing out. All right, we're going to bring those values down here. So we've got 0.001 moles of the silver ion, and we've got 0.003 moles of the carbonate. And I call this a stack, because what we're going to do to figure out which one of these two is limiting is we're going to go ahead and calculate as if these that we had one of these values and not the other one. So we're going to take each one of these independently, but I'm going to do a simultaneous calculation with one value over the top of the other one. And what we're going to do is figure out if, for example, all we had was the silver, how much silver carbonate would form. And if all we had was the carbonate, how much silver carbonate would form. We're going to compare the two values, and whichever one is the smaller value, that came from the limiting reactant. So we're solving for the silver carbonate in both cases, so I'll write that in on top of my fraction here. And then we're looking at the stoichiometry for each of the respective reactants in this. So the silver, to form the silver carbonate, the mole ratio is 2 to 1. So we have two silvers that go down here in the bottom. And for the carbonate, it's just 1 CO3 minus 2. So you can see that if we were just using the carbonate for this, we would expect to be able to produce 0.003 moles of the Ag2CO3. And if we were using the silver, we would produce 5 times 10 to the minus 4th moles of the silver carbonate. And you can see that when you compare these two numbers, that the silver is limiting. Now, what does that mean exactly? What it means is that the silver is going to be used up in this case, and the carbonate is the reactant that is in excess. So I'll write that in here. This is in excess. So what we need to figure out now, and this guy here is going to go to 0. So what we need to figure out now is how much carbonate is going to be remaining. And to do that, we use the limiting reactant. So I'm going to pull it down. So we're going to have 0.001 moles of silver. And the question I want to ask is how much of the carbonate is going to react with this. So we set up another ratio like we did to figure out our limiting reactant. And now we're going to be solving for the carbonate. And this is the amount of carbonate that's used. The ratio between the silver and the carbonate is 2 to 1, so it's going to be 2 silvers down here in the bottom. And we see that we're going to end up using the same quantity of carbonate that we produce in the silver carbonate. And that's because the mole ratios of those two things are the same. So now to figure out how much carbonate remains here, all we've got to do is take the difference. So it's going to be 0.003 moles minus 0.0005. All right, and the remaining amount that we're going to have of the carbonate is going to be 0.0025 moles of carbonate remaining, and I'll label that. This is what remains after the precipitation reaction. The stoichiometric part of this reaction happens. Now, we need the molarity of this again in order to use for the equilibrium expression. So I'm going to divide this by 0.4 liters. And so the new molarity of the remaining carbonate is 0.0065 molar. So now we can go ahead and calculate our solubility. So I'm going to rewrite the solubility equilibrium expression here. So it's going to be the Ag2CO3 in equilibrium with the silver and the carbonate. All right, we set up our box or the ICE. I'm going to put in my placeholder. The silver has gone to 0 and the carbonate is 0.00625. And I see, looking down here, that I made a typo. There should be a 2 inserted between the 6 and the 5. Sorry about that. All right. Okay. So coming back up here to the box, let's just take a minute here. This is what our situation looks like after the stoichiometric problem happened. Right? We calculated Q. The reaction had to shift left. We allowed that to happen. We formed a precipitate in the bottom of the beaker. Now we're letting our system come to equilibrium. Notice that the silver has gone to 0. So Le Chatelier says the system has to go to the right now. So some of the solid is going to dissolve in order to produce silver. The silver ion will be 2x, and our carbonate is going to be 0.00625 plus x. Now we set up our expression. All right, it's going to be 8.1 times 10 to the minus 12th. This is going to equal the 2x quantity squared, and then because we're dealing with a small equilibrium constant, we're going to drop the x out of the sum. All right, so we have this situation here, which allows us to easily solve this problem. So to simplify, we're going to have 4x squared times 0.00625, and that's going to be equal to 8.1 times 10 to the minus 12th. So going ahead and simplifying, our x value then is going to be equal to 1.8 times 10 to the minus 5th. Now, one caution here. This is our new solubility. All right. You need to compare this number back to the 0.00625 and make sure that these two numbers are suitably far apart. How far apart should they be? The bottom line is that what I normally do is apply the 5% rule to this. So I would take 1.8 times 10 to the minus 5th and divide it by 0.00625 times, okay, so let me start over. I would take 1.8 times 10 to the minus 5th and divide it by 0.00625 times 100, and that value should be not 5%. And in this case, if you run that calculation, you're going to find out it's somewhere around 0.2%, somewhere in that neighborhood. So this value is suitably small enough by comparison to this. And the only reason I bring that up is because, once again, we made the assumption to drop this x, and we need to make sure that that assumption was all right. I was pretty certain we could do it because we have a constant, equilibrium constant, that's 10 to the minus 12th. And so I'm just making sure to point that out. In this case, we were well within our capabilities to do that. So this now represents the new solubility of the silver carbonate in a situation where we combined two solutions. And with that, I'm going to go ahead and close the video.